Hi, welcome to the screencast for 10.2 and the start of 10.3. In 10.2 and 10.3, IB is talking about two groups, two homologous series known as alkanes and alkenes, which are perhaps the simplest of the organic compounds to look at. So alkanes are represented by the general formula CnH2n plus 2. Their names then end in A and E, like methane, ethane, propane. There's really no functional group, so I think of hydrogen as being the functional group because on that last carbon, typically you have CH2 and then something attached like OH for alcohols, but in this case, it's just a hydrogen in there. They're called saturated hydrocarbons, saturated meaning that the carbons all are holding 4 different atoms attached, 4 single bonds. You couldn't possibly attach another atom to it. You could substitute, you could have a single replacement reaction and bump something off, but you can't add any more bonds or any more atoms to the structure. So because of this, the carbon-carbon and carbon-hydrogen bonds are fairly strong bonds, even though they're nonpolar. So this means alkanes are going to have a very low reactivity, okay? They're also going to tend to be gases, have a high volatility or become gases quite easily. But it also means that they're very stable. So we can compress them into liquids if we want, like propane is often transported. If you've ever seen a tank that says LP gas, that means liquid propane, because you can compress it and store it and transport it pretty safely. Butane in lighters is compressed into a liquid, again, because it's pretty safe. It's very low reactivity compared to alkenes and some other things. So 2 reactions that alkanes tend to be involved in are combustion and substitution. And substitution is also known as halogenation because, or many of the substitution reactions are what are known as halogenation because halogens get added on. So IB expects you to understand the mechanisms of both. So we're going to go ahead and take a look at those starting on the next slide. So a combustion reaction, remember, just means that you're burning. And it's used widely in engines. Number one reason is for transportation, but we also use engines or motors to do a number of other jobs for us in industry. We also burn them in electrical power plants to generate electricity. This is what gets the turbine or the generator moving. And we burn them to heat homes and other places. So 2 really big critical uses for alkanes is transportation and heating. The general reaction is an alkane plus O2 equals CO2 plus H2O. And it's a highly exothermic reaction because a lot of energy is needed or released to form the CO2 and H2O bonds. So if you remember your basic enthalpy chart, you have the reactants going in and the products coming out. This is where the bond making occurs, and that's going to require a lot of energy to make those bonds, which because it's on the product side of things, it means that energy is being released. The other thing that you should realize about combustion reactions is that it produces some undesirable products. CO2 and water seem pretty harmless, but they're both greenhouse gases, which means they absorb infrared heat or infrared radiation, which is just heat, that's being reflected back towards space. So if you think about it, the sun sends in a ton of energy to Earth every day, and if Earth didn't reflect some of that energy back, the Earth would just get hotter and hotter and hotter. Well, now that we've increased the amount of greenhouse gas, most scientists agree that we're trapping more and more heat, which is definitely having some effect on our climate. It's not just global warming, it's really global change or climate change. So it's similar to a cloudy night, keeping the temperature warmer, putting a blanket around the Earth, but now we have that blanket on all the time. Some other issues with combustion reactions is that if the oxygen is limited, then you have what's called incomplete combustion, and instead of forming CO2, you could form carbon monoxide or even carbon. Carbon monoxide is a pollutant because it binds to hemoglobin in your blood in place of the oxygen, which of course is going to be a problem if you're not getting enough oxygen. It's going to lead to all kinds of health issues, or ultimately it can lead to death. You hear about people dying of carbon monoxide poisoning because they're burning a space heater within an enclosed space. And if it's really limited, if the oxygen is really limited, then burning the alkanes can form carbon, which is bad because it's a solid, so it tends to clog up your engines and such. But the soot is also very bad for your lungs. It forms air pollution or smog, and that's been linked to global dimming, which is also a unique issue that incoming sunlight gets reflected out before it can ever reach us. So we've got kind of the opposite problem going on as well. But all four products, whether it's carbon dioxide, carbon monoxide, or carbon, along with water, all of them have environmental implications. Okay, looking at the reactions for alkanes, the substitution reaction for alkane is similar to the displacement or replacement reactions that we studied earlier. And it's considered a substitution because it works with a little bit different mechanism. Now remember, alkanes are fairly stable, fairly unreactive. So having a halogen come in and substitute, even though halogens are pretty reactive, requires energy. So it's a unique process. It needs energy to do it. So halogen molecules do it by splitting the halogen molecule into two. That's called homolytic fission because UV light is used to break the halogen molecule apart. And then each halogen atom becomes a free radical, meaning it has an unpaired electron but no charge. So it's not an ion. You don't split the Cl2 into 2 Cl minus because there aren't electrons available. They haven't come from anywhere. So instead you have 2 Cls, each with 7 electrons on it. This is a free radical, meaning it's really reactive because chlorine is any of the halogens are among the most reactive of all elements. So it's going to cause a chain reaction. And a chain reaction is also unique because it means the free radicals can bond with an alkane, but it will also produce another free radical. Not necessarily the same free radical, but another free radical. And this is known as propagation. And what it means is that one chlorine atom can be split apart and it can start a chain reaction where in the ozone layer, and this happened in the late 70s with aerosols, that one chlorine atom can go on and end up breaking down 1,000 oxygen atoms before that process is ever terminated. So if it's a reaction with positive products, then a chain reaction is great. But in the case of the free radicals, generally aren't good things because they're linked to cancer and aging and the ozone destruction. Then it's not good to have this chain reaction going on. So in page 200 in your book, they talk about the mechanisms for this substitution reaction of an alkane. And they talk in depth about the 3 steps: initiation, propagation, and termination of this process. And IB will expect you to know what these 3 steps are, and they'll expect you to be able to give one equation for each of these. Well, initiation really only has 1 step, and it's really pretty straightforward because it's a chlorine atom. As I said, it's the halogen, so I'm just going to use Cl2. It's being split by UV light. UV light is considered a catalyst, not a reactant, so I just put it over the arrow. And it's going to form 2 of these free radicals. And to show that the chlorine is a free radical and not an ion, we write 2Cl, and then we put that dot there representing the 1 unpaired electron. Now remember, there are 7 electrons around chlorine, but the other 3 are paired, so they're not going to be involved in any chemical reactivity. So free radical is shown as I have here. So then the second step is this idea of propagation, which means this chlorine free radical is going to react with my halogen. And if you look in the book on page 200, there's several steps. They give several propagations that go on. But this is the first propagation. I think it's the easiest one to remember and understand because, remember, this is an alkane. So I'm going to go with the simplest alkane, CH4, reacting with a free radical. And the products have to give me another free radical plus a substitution. So what's going to happen here is this chlorine is going to take a hydrogen so that it can become HCl, and then it's going to leave behind the free radical CH3 with an open spot. Okay, so again, the propagation is because one free radical binds with the alkane or disrupts the alkane and leaves behind a free radical. So a hydrogen is pulled off to stabilize this HCl, which leaves the CH3 short an electron, or the CH3 now becomes my free radical. There's other propagation steps. You're welcome to look at those or memorize those. But again, I think this is the simplest one because we take our Cl free radical from the initiation step, we plug it in with the alkane. Pretty easy to reason what's going to happen with that. So then termination, Again, there's several steps given for termination, but I think the easiest one is just to go with the opposite of initiation. Termination is when a reaction happens that takes free radicals out of the system. So if I have two Cl free radicals, certainly they get together sometimes and recombine to form Cl2, and that would be considered a termination step because it's no longer propagating or replacing the free radical. So that's the reaction mechanism that IB expects you to be able to discuss. Moving on to section 10.3 then, 10.3 talks about a family called the alkenes, which has a general formula you notice is very similar to an alkane. It's CnH2n. So it's missing two hydrogen, and the reason it's missing two hydrogen is because now you have one carbon-carbon double bond somewhere within this compound. So methane is not possible because there's only one carbon. So ethene is our smallest alkene with a double bond between the two carbons and then two hydrogen on each of those carbons. It is possible to have more than one double bond in a hydrocarbon. If there's two, we call it a diene. If there's three, we call it a triene. But really, we're just going to concern ourselves primarily with just the alkenes, or just one double bond. So when you're naming these, you designate which carbon atom the double bond is on when it's propene or bigger, because it could be on one of the ends or it could be on a middle carbon. So you need to designate that 2-propene or 1-propene. And then the other thing to realize about alkenes is that that double bond is going to contain a sigma bond, which is pretty strong. It's the first bond formed. But then the pi bond, remember, is like a bun around the hot dog, and it has to form around that sigma bond. So it's going to be much weaker and more susceptible to being broken. So alkenes are going to be highly reactive where that double bond occurs. So alkenes also undergo addition reactions. I shouldn't say also, but they undergo addition reactions in place of substitution, because the double bond opens up and allows for two new atoms or two new species to bond onto the alkene. So think of that double bond breaking. Now each carbon has another bonding site available, and each carbon can pick up a new species. So an addition reaction results in the saturation of an alkene, and there's really four very common ones. It can be, there could be the addition of hydrogen, there could be the addition of a halogen, there could be the addition of a hydrogen-halogen combination called a hydrogen halide, or there could be the addition of water. So I'm going to take a look at the addition of hydrogen. It's called hydrogenation. It's not the same as hydration, because hydration is adding water, which we'll look at a little later. But hydrogenation is really a pretty simple process. In fact, all four of these alkene addition reactions are pretty easy because you've got your alkene. So let's go with the smallest one, which is C2H6 or CH3CH3. Remember the double, I'm sorry, it's CH2CH2 because there's a double bond between the two carbons. You have H2. And so now if we think about the two hydrogens on here, and this double bond suddenly opens up, now we have two spots where those hydrogens can bond on, and that's exactly what happens. We end up with CH3CH3 or C2H6. And so when you add hydrogen to an alkene, you simply saturate it and get an alkane. And this is a really common process in the food industry. Oils are considered to be healthier. They come from plants, and they are unsaturated fats, so they slide through your body a little easier than the saturated fats with all those hydrogens on there to cling to your blood vessels and stuff. Think about that next time you're eating chips. But it's used commonly in the margarine industry, the food industry, to make these oily fats more solid at room temperature. So like, M&Ms melt in your mouth, not in your hands. If they hydrogenate the oils or fats they're using in it, they can keep it more solid at room temperature. Now, unfortunately, it makes it less healthy. And so the same process is used to produce trans fats, and those are even worse for us. So really, when you start using soft margarines, people, you're using them thinking they're a healthy alternative to butter. In many cases, they really aren't, and in fact, in many places, hydrogenated fats and trans fats have been eliminated because people finally realized the health risks associated with it. So I'm going to stop there for this screencast, and in part B, I will look at the other three addition reactions as well as the addition reaction for polymers.